Hello and welcome to today's lecture on multiplexing techniques. And you will find that this multiplexing techniques have widespread application in data communication. Here is the outline of today's lecture. First we shall discuss why multiplexing, why do you really need multiplexing. Then we shall introduce to you the basic concepts of multiplexing, and as we shall see, there are two basic approaches of multiplexing. First one is known as frequency division multiplexing and second one is known as time division multiplexing. One variation of this frequency division multiplexing is wavelength division multiplexing, which is used in the context of optical communication. Whenever we send optical signal through optical fiber, light signal through optical fiber, then we call it wavelength division multiplexing, although basically it is same as frequency division multiplexing. Then the time division multiplexing has again two different types, the synchronous and asynchronous. We shall discuss about them in details. Then there is another technique which is known as inverse TDM, which is also used in data communication today. So, we shall conclude our lecture by discussing about inverse TDM. On completion, the students will be able to explain the need for multiplexing, that is why multiplexing is needed. They will be able to distinguish between multiplexing techniques, what are the different multiplexing techniques. They will be able to explain key features of frequency division multiplexing and also the key features of time division multiplexing. They will be able to distinguish between the two types of time division multiplexing, one is known as synchronous, another is known as asynchronous. And finally, they will be able to explain the concept of inverse time division multiplexing. To discuss about why multiplexing, let us consider the observations that we have in our day to day data communication. First one is that most of the data communication devices typically require modest data rate. As we shall see, normally when we send data, an individual user requires very small bandwidth. For example, whenever we send voice, we require a bandwidth of maybe up to 4 kilohertz or sometimes 3 kilohertz. Similarly, when we send data, that time also we may not require high bandwidth. On the other hand, the communication media which are usually used today nowadays have much higher bandwidth. For example, if we use coaxial cable or optical fiber or if we use microwave technique, then the bandwidth of the medium is quite high. So, whenever two users are communicating through a link, usually the full capacity of the link is not utilized. So, how do you make full utilization of the link capacity? And in fact, as we shall see, higher the data rate, the most cost effective is the transmission facility. That means, to make the transmission facility cost effective, we want a medium which has high data rate, high transmission capacity. On the other hand, the individual users have smaller capacity. Based on this observation, the multiplexing techniques have developed. Basically, it can be used when the bandwidth of a medium is greater than individual signals to be transmitted through the channel, in such a situation, that means, since the bandwidth of the individual signals is small, then a medium can be shared. This is the key idea, sharing by more than one channel of signals by using multiplexing. That means, what you are trying to do, we are trying to share the bandwidth of a channel by a number of users. Just like in a city, the water comes through a bigger pipe, and that water gets distributed through narrower pipe to individual residences. It is somewhat like that, and for efficiency, the channel capacity can be shared among a number of communicating stations. That means, this also increases the efficiency of communication of the transmission media. And since we are concerned about the cost, you will find that most common use of this multiplexing will be in long haul communication using coaxial cable, using microwave, and using optical fiber. So, these are the three transmission media which have quite high bandwidth and which are used for long distance communication, and there we should make use of the bandwidth in a very efficient manner, and that is where we can use multiplexing. Let us take up a very simple example, even when the bandwidth is not really very high, say telephone line. In a telephone line, as you know, the analog telephone line has got bandwidth, very small bandwidth, and out of which about 2400 hertz can be used for data. Now, even this small bandwidth can be shared for data communication in two direction, as it is shown in this diagram. The first part 600 to maybe 1800, this is 1800, that means up to 1200, 600 to 1800, then 1800 to 3000. So, 600 to 1800, this part is used for data communication in one direction, maybe from user A to B, and the other one can be used from user B to user A. So, we see that even this small bandwidth can be shared by making use of this multiplexing, and here the multiplexing can be made possible by using the encoding the data by using, say, PSK, phase shift keying. So, PSK increases the data rate with a smaller bandwidth, smaller baud rate. So, even with 2400 hertz bandwidth, the data rate can be quite high. So, this is a simple example. This can be used for bidirectional communication between two users using the same telephone line. Now, let us look at the basic concept of multiplexing. Here we use a device known as multiplexer. Here you see we are using a device known as multiplexer. This multiplexer is combining the signals coming from n channels. As you can see, this is channel 1, this is channel 2, and this is channel n. So, from n channel signals are coming, and it is combined with the help of a multiplexer. Then the multiplexer is sending the combined or composite signal through a single medium. So, you have got only one medium, and the signals of n channels are being sent through the medium. And at the other end, we have a opposite device known as demultiplexer. This demultiplexer separates out the signals of different channels by using filtering, and here we get back the signal corresponding to channel 1, signal corresponding to channel 2, and so on up to channel n. So, by making use of two devices, one is known as multiplexer, which combines signal of n channels into a single composite signal, which can be sent through a single medium, and at the other end a demultiplexer separates out the signals from different channels and can be sent to different stations. So, this is how the multiplexing and demultiplexing can be done. Now, as I mentioned, there are two basic approaches. First one is known as frequency division multiplexing, and as we shall see, frequency division multiplexing is possible because of the analog transmission that we have that is possible by using modulation. As you have seen, the modulation performs narrow banding of the signal. As a consequence, it is possible to send n different signals, each of them having a small fraction of the bandwidth through the transmission media. So, here what you are doing, the n channels are multiplexed and you are creating a frequency division multiplexing, and here we are sending all the n different signals simultaneously, and obviously they should be at different bands, so that one does not mix with other, and at the other end again by using filtering we can separate out the different channels at the other end, say channel 1, channel 2 and channel n. So, this is frequency division multiplexing. Here everything is being sent in parallel. The second one is time division multiplexing. Here the approach is a little different. In the previous case all the signals were sent simultaneously, but here it is not so. As you see, the signals are coming from different channels, and what is being done, the time is divided into slots, and in each slot, in slot 1 signal from channel 1 is sent, and in slot 2 signal from channel 2 is sent, in channel 3 signal from channel 3 is sent, in slot n signal from channel n is sent. So, here it is not really all are not sent in parallel, but as you can see one it is the signals from different channels are sent one after the other in a sequence, and each is sent in a particular slot of time, and at the other end they can be again separated by reading data from this slot to channel 1, the data from slot 2 to channel 2, and so it is somewhat like a switch. It first this switch first selects this one and transmits, then it selects this one and transmits, then it selects this one and transmits, and similarly other end it performs the opposite operations. First this signal is sent to channel 1, then to channel 2, then to channel n. In this way it goes on. So, this is your time division multiplexing. Now, as we shall see, the multiplexing will require two different signaling. As I have mentioned, analog signals are used for frequency division multiplexing and also for wavelength division multiplexing, although basically they are same thing, but this is used in the context of transmitting through optical fiber. On the other hand, digital signaling is used in time division multiplexing, which has got two different versions. One is time division multiplexing, that is your synchronous, this is essentially synchronous, and the another one is asynchronous time division multiplexing, in which we use digital signals. So, this approach, the frequency division multiplexing, makes use of analog modulation techniques, and this time division multiplexing makes use of the encoding techniques that we have discussed. Let us see how the frequency division multiplexing is implemented. What is being done? The available bandwidth of a single physical medium is divided into a number of smaller independent frequency channels. So, the smaller frequency channels, the available bandwidth is divided into a number of smaller independent frequency channels. Look at this figure, smaller and independent frequency channel. So, they should not overlap with each other. Then using modulation, independent message signals are translated into different frequency bands. As we have seen, by using modulation technique, that can be done, because modulation allows narrow banding, and by narrow banding they can be translated to different frequency regions, frequency bands, and all the modulated signals are then combined into a linear by using a linear summing circuit to form a composite signal for transmission through a media. And obviously, you will require a number of carriers to modulate the individual message signals, which are known as subcarriers. So, this is illustrated with the help of, as we shall illustrate it with the help of example, and we shall make use of different modulation techniques. We shall make use, sometimes we shall make use amplitude modulation, sometimes we shall make use angle modulation, which has got two types, as we know, frequency modulation and phase modulation. Let us see how it is being done. Similarly, the for your, when the signal is digital, then we have to make use of amplitude shift keying or frequency shift keying or phase shift keying. And as we know, the amplitude shift keying and frequency phase shift keying can be combined to form the quadrature amplitude modulation, QAM. So, these are used whenever the data is digital data, and we would like to convert into analog signal, which has to be done whenever we want to do frequency division multiplexing. Let us see how it is being done. So, here the signals are coming from different sources, source 1, source 2 and source n, and here you have got the modulator, and as you can see different subcarriers F1, F2 and Fn. So, these are the subcarriers are used to modulate different signal, and if this is the bandwidth of the modulating signal and the bandwidth of the modulated signal is shown here, it is around that carrier on both sides. As you know, if the bandwidth here is B of the signal source, analog signal, then bandwidth of the modulated signal, as you know, is 2B. And after these are combined together, as you can see, total bandwidth is summation of the individual bandwidths. So, F1 plus, that means this 2B plus 2B, 2B in this way, and obviously the separation, there should be some separation between F1, F2 and Fn, so that there is no overlapping. So, this is the transmitted signal bandwidth. As you can see, the transmitted bandwidth is sum total of the individual bandwidths of different signals, and at the other end that composite signal is received and then demodulated. Demodulation is nothing but some kind of filtering, and here individual filters are having are essentially band pass filter having central frequencies F1 for this case, in this case F2, in this case Fn. So, you can see these are the filters, and then after doing this demodulation and filtering, these signals can be sent. Then of course, you have to do that signal has to be converted back into, actually this filter should be here, I believe it has got interchange, filter should be here and demodulator should be here, the figure has got interchange, and so demodulate, after demodulation we get the original signal which has to be sent to the destination. So, this will be here and this will be here. Okay. So, this is how the frequency division multiplexing is done, and as I mentioned, there should be some separation between different frequency bands. So, this is corresponding to the channel 1 with subcarrier FC1, and this is the band, this is corresponding to bandwidth of the channel 2 FC2 and so on. In this way, you have got channel n with subcarrier frequency FCN. Now, as you can see, between each band there is a small gap, and this is known as guard band. This guard band is necessary so that the channels channels must be separated by strips of unused bandwidth, that is your guard band, to prevent inter-channel crosstalk. So, if there is no separation, there is a possibility of crosstalk, since they are very if you place them side by side without any separation, there will be some overlap which will lead to crosstalk. So, we have to avoid crosstalk, these guard bands are used, and obviously it is an extra overhead. So, apart from the sum total of the bandwidths, some additional bandwidth is wasted for these guard bands. This is an extra overhead that is used in frequency division multiplexing. And this frequency division multiplexing has many uses, as we know. For example, the transmission of AM and FM radio signals. Every day we are listening to AM amplitude modulated, that AM radio stations, and FM radio stations. FM has become very popular because of the quality of the signal nowadays, and both are based on frequency division multiplexing, FDM. And our TV broadcasting is also based on frequency division multiplexing, because you have different TV stations and they use different bands for transmission of their signals, and in the TV, that receiver, we can select different channels with the help of the filtering. And also we are familiar with cable television, where the signal is distributed with the help of coaxial cable. Later on we shall discuss about it in more details. There also we use frequency division multiplexing. So, these are the three important areas where frequency division multiplexing is used, and nowadays cable television is used not only for signaling video. Cable modem, cable television of cable modem can be used for the transmission of data. Then, as I mentioned, there is one special special type of multiplexing, frequency division multiplexing, is called wavelength division multiplexing, whenever we are sending light signals through optical fiber. And this why we call it wavelength division multiplexing? The reason is the frequency is very high, so wavelength is small. So, instead of stating in terms of frequencies, we state in terms of wavelengths, and particularly this wavelength division multiplexing is becoming very popular because of the enormous bandwidth provided by optical fiber medium. And to make use of the enormous bandwidth, wavelength division multiplexing is the most viable technology that overcomes the huge optoelectronic bandwidth mismatch. As I have told, the optical fiber can send very high bandwidth. On the other hand, individual users who are sending either audio or video, their bandwidth requirement is smaller, and only by using wavelength division multiplexing we can share an optical fiber, and we can make use of the huge bandwidth mismatch, or make use of the enormous bandwidth, and it also overcomes the huge optoelectronic bandwidth mismatch. And wavelength division multiplexing optical fiber network comprises optical wavelength switches or routers interconnected by point to point fiber links. Later on we shall discuss about it, and end users may communicate with each other through either all optical wavelength division multiplexing channels, which are known as light paths, which may span over more than one fiber links. That means, over a very long distance the signal can be sent in the form of light, and at the other end with the help of suitable transducer, as we know that we can use the diodes, pin diodes, for conversion from light signal to electrical signal, and then get back the original data. So, the basic approach, as you can see, is same. Here you have got a number of sources, n sources coming 1, 2 and n, and here is the bandwidth of the optical signal, and these are multiplexed and getting the this is the bandwidth represented in terms of wavelengths. This is the bandwidth of the first signal, lambda 1 to lambda 2, then lambda 3 to lambda 4 coming from source 2. In this way, lambda 2n minus 1 to lambda 2, that is coming from source n. So, these are expressed in terms of wavelengths, but essentially these are small frequency ranges, and these light signals are transmitted through optical fiber. So, here you can see the bandwidth is much more, which can be easily sent through optical fiber, and the optical fiber, with the help of demultiplexer, we can separate out different optical signals having different frequencies, and then they can be sent to destinations. you may be wondering how really it can be done, this multiplexing and demultiplexing. This can be explained very easily with the help of this simple diagram, where we have used two prisms. As you know, optical signal, the light signal has two properties, reflection and refraction. So, we can make use of the refraction property to combine light signals coming from three different sources. Then as you can see, a single composite signal is here, which can be sent through optical fiber through this region, and at the other end with the help of another prism they can be separated out, and we can get back all the three different signals. So, this is how the wavelength division multiplexing can be done. Now, let us focus our attention to time division multiplexing. As I mentioned, time division multiplexing is used when we are using digital signals, and digital signals as you know are generated by different encoding techniques. We shall discuss about them in details. We have already discussed about them in details. This time division multiplexing is possible when the bandwidth of the medium exceeds the data rate of the digital signals to be transmitted. And here also, that means here there is a possibility of sharing. Then multiple digital signals can be carried on a single transmission path by interleaving portions of each signal in time. So, what we are doing essentially, we are interleaving signals. First we are sending signal from channel 1, then signal of from channel 2, then signal of channel 3. In this way we are interleaving, then we are sending it through the medium having higher bandwidth. This interleaving can be done at the bit level or in the block or by blocks of bytes. That means we can take one bit of from channel 1, then one bit from another channel, then one bit from another channel. We can do it this way. This is called bit level interleaving. Or we can take one byte from channel 1, then a second byte from channel 2, then the third byte from channel 3, and so on. So, this way we can do interleaving in terms of bits or in terms of blocks of bytes. And obviously, in this case, as I told, we shall be using digital signal, and digital signals are generated by using suitable encoding technique. We have already discussed about that. If the data was digital, digital signals are generated by using three different types of coding: unipolar, polar or bipolar. Similarly, if the original data was in analog form, then digital signal can be generated by using pulse code modulation or delta modulation. In either case, ultimately we have got digital signals. These digital signals, as you know, is expressed in terms of bits per second or kilobits per second, that is the data rate, and these digital signals can be sent through a medium by using time division multiplexing. However, this will require some kind of buffers. The incoming data from each source are briefly buffered, and each buffer is typically 1 bit or 1 character in length, depending on the interleaving level, as I mentioned. The buffers are scanned sequentially to form a composite data stream. So, by sequentially scanning the different bits, a composite data stream is created, and the scan operation is sufficiently rapid, so that each buffer is emptied before more data can arrive. So, let us see how this is being done. Say here you have got data is coming from source 1, source 2, source n. So, as if there is some kind of switch, you are taking from this source, then from this source, in this way you are taking, and we are creating a frame. So, as you can see here, in this frame, first we have got the data from source S1, then from source S2, then source S3 and so on up to S minus n. After taking data from n sources, again it is started from source n S1, as you can see here, second frame is started, and then from source S2, then from S3 and so on. Then this is sent in terms of time. So, this frame is sent, then this frame is sent, and so on. So, as you can see here, there are n slots in each frame. So, this is slot 1, this is slot 2, in this way you have got n slots, and each slot corresponds to a particular source. That means, slot 1 corresponds to data from this source, slot 2 corresponds to data from this source, slot n corresponds to data from this source. However, whenever we are doing the framing, it is some additional bits are necessary for synchronization. Usually, per frame one bit is used for the purpose of synchronization. So, a special bit or bit pattern is added in a control channel. So, this is used for synchronization. For example, for each frame, if this is the frame, at the beginning of each frame a 1 is added, then if it is the next frame, at the beginning of this frame a 0 is added. In this way, alternately ones and zeros are added for the purpose of synchronization, and these bits are used for the purpose of synchronizing a frame. Essentially, these synchronization bits states that this is the beginning of a frame, and the different slots, data from different slots has to be taken from are coming from different sources, and they are demultiplexed at the receiving end. However, sometimes the data rate from a particular source does not match or is not multiple the rate at which the scanning is done while doing multiplexing. In such a case, some additional bits are added, which is known as pulse stuffing or bit padding. Both the terminologies are used to facilitate synchronization of different data rates. For example, you are sampling at the rate of say 8 kilobits per second. So, here data is coming at the rate of 8 kilobits per second, but suppose here it is coming from 8 kbps, but here it is coming at the rate of 7.2 kbps. So, obviously, these two cannot be synchronized. So, what is done, additional bits are stuffed into this so that the data rate for this is 8 kilobits per second, and then at the receiving end those dummy bits are taken out or separated out, because it is known that the data from this source is coming at the rate of 7.2 kilobits per second, and so those extra dummy bits can be taken out. So, this is known as pulse stuffing or bit padding, so that the signals from different data sources having different data rates can be combined by using time division multiplexing. So, this is your pulse stuffing or bit padding. Here is an example of synchronous time division multiplexing. So, here for example, here is the transmitter, data is coming from 4 sources. Say this is the source 1, this is source 2, this is source 3, this is source 4. And as you can see here, source A has got 4 characters to be sent, has 4 characters, source B has got 3 characters, source C has 2 characters, and source 4 has only 1 character to be sent. So, as you do the framing, the first frame has got 4 characters coming from 4 different sources. So, here you have put A coming from source A, then you have put B in slot 2, this is corresponding to second frame, then here you have put C coming from third source and D coming from fourth source. So, this is how the first frame is created. Now, as you go to the second frame, the second A is put here in the first slot, then second B is placed in the second slot, then second C is placed in the third slot. Here as you can see, there is no data, this slot goes empty. And when we go prepare the third frame, the first 2 slots are filled up by the third characters from source 1 and source 2 respectively. So, here in slot 1 from this third character A, and in the second slot the third character B, but these two slots remain empty because there is no data. And at the receiving end, however, they can be received and they can be sent to different sources. As you can see, as it is coming, this A will go here, this B will go here, this C will go here, this D will go here. So, there is no problem in multiplexing and demultiplexing. The problem is somewhere else. What we are observing in this particular case, the data that is coming from that is generated by framing has got some redundancy. That means, if a particular source has no data to be sent, that particular slot goes empty, because each slot is dedicated for a particular source. So, in this case, as you can see, in frame 2 one slot goes empty, in frame 2 two slot goes empty, and in frame 3 3 slot goes empty. So, this is essentially wastage of bandwidth, because here as you can see the bandwidth of this medium is higher, which is this composite signal is sent through a medium which has higher bandwidth. So, you can the data rate here is much higher than these data rates. So, the transmission media having higher bandwidth is used for sending multiplex signal. However, in synchronous time division multiplexing, as we find the bandwidth is not fully utilized, there is some wastage of bandwidth. So, this wastage of bandwidth we have to overcome this problem. This is the limitation of synchronous time division multiplexing. As I have seen, many of the time slots in a frame may be wasted. This problem is overcome by using a new technique which is known as statistical or asynchronous or intelligent time division multiplexing. Actually, there are 3 different names to refer to the same thing. So, it is referring to asynchronous time division multiplexing, but sometimes it is called statistical time division multiplexing or intelligent time division multiplexing. So, in this asynchronous time division multiplexing, slots are allocated dynamically on demand. In the previous case, as you have seen, the slots are pre-assigned, dedicated to each channel. Here it is not so. Depending on whether a particular channel has some data or not, a slot is allocated dynamically. So, no slot is assigned to a particular source. Any slot can be used by any source, and it takes advantage of the fact that not all the attached devices may be transmitting all the time. For example, whenever we talk over telephone line, all the time we are not speaking, sometimes we are listening, sometimes we are thinking. So, that silence period is wasted whenever we talk through telephone line. So, that wastage can be overcome by using statistical time division multiplexing. Let us see how it can be done. This is illustrated with the help of this simple example. Here data is coming from 4 different sources A, B, C and D, and here you have got the high speed multiplexer. Here obviously the data rate is 4 times that of the data rate of these inputs. Now, so here there are different time slot. So, this is corresponding to going to source A, this data is going to source B, this is going to source C, and this is going to channel source or channel D. Now, as you can see, during time during this time slot T0 to T1, only channel A and channel C has data. Similarly, during slot 2, channel B, channel C and channel D has data. during slot 3 channel B and channel D has data, during slot 4 channel A and channel C has data. So, if we use synchronous time division multiplexing, the framing will be done in this way. In frame 1 we shall have the this data, this is A1 and C1. In frame 2 we shall have B1, C1 and D1. In frame 3 we shall have B2 and D2, as you can see B2 and D2, and in frame 4 we shall have A2 and C3. And we can see these are the time slots which are wasted. Although we have large bandwidth from here to here, the bandwidth is quite high, we are not making use of it. Let us see what we can do in synchronous time division multiplexing. The synchronous time division multiplexing, in synchronous time division multiplexing we reduce the bandwidth. So, instead of 4 slots we have only 2 slots coming out from this multiplexer. So, we have got in a frame we have got only 2 data. So, in the first frame we are sending A1 and C1, in the second frame we are sending B1 and C2, in the third frame we are sending D1 and B2, in the fourth frame we are sending D2 and A2, and then in the fifth frame C3. So, we see that wastage is much less, and the remaining slots here, these frames and slots can be used for sending data coming from the other time slots. So, we are making much better use of it, the available bandwidth. And so, in this asynchronous time division multiplexing, since the data arrive from different sources are arrive from and are distributed to IO lines unpredictably, address information is required. You see, there is a problem in this. Although we are able to make use of the bandwidth in a more efficient manner, or we can say in a different way, with a transmission medium of lesser bandwidth we can send signals coming from different sources, provided they do not generate data continuously. However, there is a problem. At the receiving end it is necessary to identify which data is coming from where. For example, at the receiving end this slot is not meant for only data from source A1, source A, or this is not meant for source B. So, data in this slot data can be sent by any one of the channels, or data can be taken from any one of the channels. At the receiving end, how the receiver will know that data of a particular slot belongs to a particular channel? For that purpose you have to incorporate address information. So, for proper delivery at the receiving end it is necessary to have address information embedded as part of the data. So, there is an overhead. So, apart from data, as you can see here, we are adding the address information, and since it is an overhead we want to minimize it. If we are sending say one source per frame, then we can do the framing in this manner, data and address that we can send in a particular frame. Whenever we are sending multiple there is a frame coming from multiple sources, we shall also require address information and length of data if we use variable length data coming from different sources for each of the sources. So, for each of the sources we require address, length and data. That was not so in synchronous time division multiplexing. There the number of bits to be taken was fixed and the slot allocation was fixed. Here it is not so. So, these additional information that is needed to be sent through the transmission media has to be minimized, and to do that sometimes we make use of relative addressing, so that the number of bits required to specify the address is smaller whenever we use relative addressing. And sometimes we can use fixed length, or length also can be specified in some special way, so that the length field is smaller, so that the efficiency of asynchronous time division multiplexing is more. In asynchronous time division multiplexing, the data rate at the output is less than the data rate at the inputs. We have seen that the data rate at the inputs is higher than the data rates at the output. How? Because the inputs are not always sending data. However, in peak periods the input may exceed the capacity. Because the output bandwidth is smaller than the sum total of the input bandwidth, in peak periods there will be some kind of overflow, it will exceed the capacity. How can we overcome this? To overcome this, we can use buffers of suitable size to store the data, then they can be sent, they can be selected at later time slots. So, some experimentation has been done by which one can decide what should be the buffer size for achieving efficiency. Let us assume there are n is the number of inputs, r is the data rate of each of the source, m is the effective capacity of the output, and alpha is the mean fraction of the time each input is transmitting. That means, the sources are not transmitting all the time, that is the important property that we are exploiting, and obviously the alpha is less than 1, it lies between 0 to 1. Then a measure of the compression, that means the bandwidth of the transmission media compared to the maximum bandwidth that is required, that is the value of C. M is the effective capacity of the output, and N into R is the maximum bandwidth, because you have got n sources and R is the data rate of each source. So, you see this factor is again less than 1 and it lies in the range alpha to 1. So, C lies alpha to 1. So, depending on the statistical behavior of the inputs, the value of alpha and value of C will depend. That is the reason why it is called statistical time division multiplexing. So, we have discussed the frequency division multiplexing, we have discussed time division multiplexing. Here we have another very important technique which is known as inverse multiplexing. This is opposite of the multiplexing technique. In the previous case, what was done? The individual inputs were of lesser bandwidth, then we are combining to form a composite signal of higher bandwidth. Here it is the opposite. Here we are receiving signal of higher bandwidth, then it is divided into a number of channels of smaller bandwidth, and at the other end the opposite operation is done. In what situation it can be used? Let us see an application. Suppose you have to send say voice, which will typically require 64 kilobits per second. Then let us assume you have to send data, which will require say 128 kilobits per second, and video, which will require say 1.544 megabits per second. Now, the user can hire a medium of transmission capacity 1.544 megabits per second. Then whenever it wants to send video, it will make full use of the transmission bandwidth. However, whenever it is sending data, that bandwidth is not utilized, or whenever it is sending voice, the transmission bandwidth is also not utilized. Let us consider the other alternative. The other alternative is that here you have got channels of a number of channels of smaller bandwidth, and these bandwidths say it is only 64 kilobits, and you have got a large number of 64 kilobits per second bandwidth available here, and which are available on demand. So, here we are making use of the property bandwidth on demand. So, whenever we are sending voice, only 64 kilobits per second bandwidth is demanded and one channel is assigned. Whenever we are sending data, two channels are made available to send 2 kilobits per second, and obviously we are doing some kind of demultiplexing, dividing this data into two separate channels and sending, and at the other end again we are combining. Whenever we have to send video, we will require a number of channels which are demanded, and the video data is divided and sent through a number of channels, and at the other end they are combined to get back the data. So, here we see here there is a more cost effective use of the bandwidth, and the facilitator is providing you bandwidth on demand, and as a result as and when the bandwidth is required, that is being utilized, and that is why this technique is known as inverse multiplexing, and nowadays this kind of facility is available. So, we have discussed various multiplexing techniques. Now, it is time to give you the review questions. First question is, in what situation multiplexing is used? Second question is, distinguish between the two basic multiplexing techniques. Third question is, why guard bands are used in frequency division multiplexing? Fourth question is, why synchronization pulse is required in time division multiplexing? Fifth question is, what limitation of time division multiplexing is overcome in asynchronous time division multiplexing, and how? Sixth question is, design a time division multiplexing system having output bandwidth of 128 kilobits per second to send data from 4 analog sources of 2 kilohertz bandwidth and 8 digital signals of 7200 bandwidth. Here we see we have to do pulse stuffing, bit stuffing, so that the synchronization is possible. So, the answers of these questions will be given in the next lecture. And here are the answers to the questions of lecture 10. First question was, which modulation technique is used in optical communication? As we know, on-off keying is used in optical communication. It is some kind of amplitude modulation technique. It is a special case of amplitude modulation or amplitude shift keying, ASK technique. Amplitude shift keying, which is known as on-off keying, is used in optical communication. Then what are the three modulation techniques possible in modems? We shall discuss about modems in detail later on. The three modulation techniques are amplitude shift keying, frequency shift keying, and phase shift keying. We have discussed it in detail in lecture number 10. Then the third question was, why phase shift keying is preferred as the modulation technique in modems. In PSK scheme, it is possible to send signal having more than one digital value. The approach is known as quadrature PSK. That means here the baud rate is less. Baud rate is less than the data rate. As a consequence, we can send more data through a transmission medium of smaller bandwidth. That is why PSK is preferred. Fourth question was, out of the 3 digital to analog modulation techniques, which one provides higher data rate? Answer is, for a given transmission bandwidth, higher data rate can be achieved in case of PSK. In other words, in PSK, higher channel capacity is achieved although the signaling rate is lower. So, that is the end of all the questions. So, we have discussed various multiplexing techniques. As I told, the multiplexing techniques have widespread application in different areas. In the next two lectures, we shall discuss about the applications of multiplexing like telephone system and so on. Thank you.